Hey folks, this is a surprise fourth video of this section because I forgot to talk about this during the gravitation video, and that gravitation video was too long anyway. So here's a final video of this section about gravitational field strength, in other words, little g. And so we'll get right to it. So this is a way to make sense of where little g comes from. So we're going to start on a planet. So on a planet's surface, your weight is actually calculated two ways. We have the force of gravity on you is your mass times the value of little g. And your weight is equal to the gravitational constant times the mass of the planet you're on times your mass divided by the radius of that planet squared. So when you're standing on the surface of a planet, this value of r represents the radius of the planet. Now, typically in physics, the lowercase version of a variable is the variable itself. So this is any distance between centers of mass. If it's a specific radius or a specific value, it often is changed to a capital R. So I'm going to use a capital R from here on out. Basically, if you were on a planet's surface, both of these are equivalent. So I can write them as equal to one another. M times G, little m times G, equals big G times big M times little m over R squared. And you will notice that the variable little m appears on both sides of this equation. So I can divide both sides by m, and that goes away. And I get this equation of little g equals the gravitational constant times big M times R squared. So big M is going to be the planet mass, and big R is going to be the planet radius. And so all I wanted to do was just show you an example of how you would use this. And basically you're going to use this to compare the gravity strength on different planets. So if we have planet A, where the mass of the planet is m and the radius of the planet is r, we're going to compare that to planet B, where the mass of that planet is 3m and the radius of that planet is 3r. So it's both bigger and more massive, bigger volume and bigger mass. So for planet A, little g on planet A is equal to g big M over r squared. So that's just an expression for planet A. For planet B, we're going to derive the same type of expression. This time it's big G times 3m over the quantity 3r squared. And I'm just going to do a little bit of math. We've done this a little bit in class lately, and so maybe this is sunk in already. But these integers, I'm going to bring them out front, and I'm going to do 3 over 3 squared, which is 9, times the letters, right? Basically the values that are constant. So little g on planet B is 3/9 g big M over r squared. And if I look over here, planet A's value of little g is gm over r squared. So I can condense that and say that little g on planet B is equal to 3/9 little g on planet A. I'm going to clean that up a little bit more. 3/9 is the same thing as 1/3. So the value of little g on planet B is 1/3 the value of little g on planet A. And I chose these numbers as an example to show you that even though planet B is more massive, it is also much larger, 3 times the radius. And so that actually contributes more to the difference between them. It means that radius is a more important variable when you're considering how strong gravity is. And so the fact that it's triple the mass, but also triple the radius, brings its value of g down below that of the first planet. So that's just one example of how you can use this little g equation. This one is not in your equation sheet, so you might want to memorize it. It's really easy to memorize. If you just take the little m away from the gravitation equation, it becomes an equation for little g. And that's it for this section.